So hi everyone, how are you? I hope you're doing awesome today. We're so excited. I'm honestly so happy. At Girls in Quantum, we're also really enthusiastic on hosting this webinar for you and for everyone that will be afterwards listening to this and seeing this in our YouTube channel and other social media platforms. So yeah, my name is Lisa and I'm the founder of Girls in Quantum, and so happy that today with Myron and IEEE Patras, we could organize this wonderful webinar for you about how to program your quantum computer. So this is a wonderful opportunity for you to learn and discover, perhaps also ask questions. Don't worry about asking many questions at all. I'm sure we will both be happy to answer those. And also, well, Myron afterwards will share with you his contact sort of information, so you can get in touch as well, connect through LinkedIn, and all of that as well. So we'll be more than happy to do that. So yeah, I think that just for the introduction, we want to both present our teams, since they are like crucial for this organization of this webinar. So as I mentioned before, I founded Girls in Quantum, and now I have a wonderful co-founder, she's Sabina, from the US. I'm from Chile. I'm currently a high school graduate, so I'm still learning a lot, and I'm really looking forward. That's why to this webinar, to learn more. And yeah, so we have a wonderful team of more than 20+ students that are all around the world. I have some connected to this webinar actually in their classrooms, so it's just great to see that they are right now in their sort of joining here and in their classrooms of their schools, gathering other students as well. So yeah, we have some people as well, for example, Dia, Maria, Cristobal from other countries as well, Europe, Chile, and also, well, India as well. So really happy, really looking forward to that. We've been organizing several seminars this year. We also hosted or launched sort of this chapter in certain colleges and universities in India and sort of here in Chile as well. So we're really happy and looking forward to this webinar as well. So yeah, without further ado, I'm so happy with the team and with all the organizations, because right now I'm here, but behind all of this is also two teams. And now I think it's your turn, Myron, to introduce your wonderful team as well. So yeah.
Yes, can you make me host so I can share my screen? And great, I hope everybody can see the presentation. I am Myron Yanakis. I am the coordinator of quantum computing and scientific group of the IEEE branch of the University of Patras. And I'm here tonight, whatever time it is, with my team to first of all introduce ourselves, and before that introduce IEEE to everyone. IEEE is the Institute of Electrical and Electronic Engineering. It's the world's largest technical professional organization dedicated to advanced technology and helping benefit the humanity from it. And IEEE is organized into some divisions. First of all, some local sections within different geographic regions. Then there are the chapters comprised of local members with similar technical interests, the societies and technical councils that compose technical divisions. And then there are the student branches at a lot of colleges, universities around the whole world. And these branches have some chapters or special interest groups and a lot of different groups like that. And that's exactly what we are. We are the student branch of IEEE of the University of Patras. We are a team of student volunteers organized in some committees for human resources, public relations, fundraising, and we have some organized chapters, 3 big societies of chapters that are the Computer Society, the Biomedical Society, and the Power and Energy Society. Under its chapter, I'm sorry, under its chapter, there are some different scientific groups that meet weekly or monthly, depending on what they are organizing at that time. And me, I'm the coordinator of quantum computing scientific group that has to do with everything about quantum computers, quantum programming, and quantum information. And you can find more info about all of this here. You can also join if you are in Patras, if you are a student of the University of Patras. And don't worry about that getting out of the screen now. In some time, you're going to have time during the break to sit and join and speak with everybody that is there in the classroom. So I think I pass it back to you, Elise, and you can continue with your presentation.
For sure, yeah, no, I think that, so you have to make me host right now.
Yeah, I'm sure I do, but I'm not sure how. Wait a minute.
Okay, awesome. So I will now share a little about us here. Okay. So I'll make it a little bit shorter this time. So screen. Okay, awesome. Let me know if you're able to see this. Okay, so I'll tell you a little bit more about Girls in Quantum as well. So as I mentioned before, I founded Girls in Quantum, and this was specifically to sort of engage with other students. I think that quantum computing is, it's really important technology right now, but also the fact that being able to share that with other students is not that really common, talking about it as well. Sometimes we hear about artificial intelligence, machine learning, and different technologies as well, but quantum computing is still a topic that needs to be sort of discussed. And that's why we have this purpose of connecting with other students and sort of democratizing quantum computing education. We're so happy so far that we've been able to sort of impact other students through creating more than 200 educational resources. And what we want to do is that even if it's a little bit, or it can sound a little bit ambitious, is to be the next Khan Academy of quantum computing, so we can have people joining everywhere around the world, joining to the platform and sort of starting learning about quantum computing, quantum algorithms, and different topics that will be also discussed today. So yeah, we have three main pillars. So we inspire, connect, and collaborate. We love to go to schools. We love to have these sessions and webinars, not just in person, but also online, so we can connect with them no matter sort of physical barriers. Connecting with others. I think that right now what we're doing, these partnerships is great to collaborate with other companies, organizations, a student also group that encourages other people to join in quantum computing. And in the case of Connect, is to create a community. I think that sometimes when we want to learn something, we're like, okay, I'm going to learn something, but we often feel discouraged because we're studying by ourselves. However, we want to create this community, so I completely invite you to join us. We have different supporters as well, my team as well, as I mentioned before, and here's some of the content that we've done. So here's, I don't know if you're seeing my mouse, but here's like some people that have been a really sort of role model for us, some of our content about single qubit quantum gates and their matrices, but also in some simple terms as well, we also have different sort of opportunities, and this has been also some of our webinars as well. So yeah, I think that we have different things coming up, but also I want for you to keep in touch. So this is our sort of our website, so you can look at us, see what we've been doing, and also our email is the same, girlsinquantum.com at gmail.com, so you can also be contacted. But we'll also provide that as well as Myron during the break, so you can be in touch with us. But yeah, I think that was like a brief introduction because I want this session to be focused on the most important, the content that Myron will teach. So yeah, so happy about that and looking forward now for the presentation.
Okay, great. I didn't expect it to be so fast, so I have to present right now and wait a minute so I can prepare everything and share my screen.
I'm my host. Yeah, I really want to be brief because I talked about your project before, and I'll talk in the end as well a little bit. But yeah, so looking forward to the meeting.
Great, that's great.
Oh, and sorry to interrupt. Just for everyone that may have questions during the session, perhaps Myron won't be able to respond them during the session, but I will gather all those questions that you may have. You can ask me personally through the chat, and I can afterwards mention those to Myron and his team, and he may be able to respond those. And if not, you can also get in touch with us. But we'll make sure that to respond all of your questions.
Yes, exactly. It won't be very easy to interrupt whatever we're talking about to ask and answer questions. But at the end, when me and the other people from my team, I'm going to introduce them right now, when we finish everything that we have to talk, we will be more than happy to give you 5, 10, even more time, even more minutes if you want to ask any questions. In the meantime, you can write in the comments or send them to Elisa to ask them for you. Anything is fine for me. So, first of all, thank you very much for the opportunity to organize this event in partnership with IEEE, with our branch of the University of Patras and Girls in Quantum. And let me introduce now my smaller team, not the whole IEEE of the University of Patras, but the scientific group that talks and meets every week, every month, whenever we find time to talk and discuss and create things about quantum computing and quantum programming. We are 4 students from the University of Patras. I'm Myron Giannakis, and along with Ioanna Giannakopoulou, we are students from the Faculty of Electrical Engineering. And Orestis Makris is from the Computer and Informatics Department, and Concetta Freri is from Material Science Department. What connects all of us from these different faculties, different departments, even different schools, we're not all in the engineering school. What connects all of us together is our passion about quantum mechanics and quantum computing, and our eagerness to learn more and share the most of the knowledge that we can with students from our university and other places around Greece and around the world. So today's talk, I think, do you still see the first slide with all the names?
Yeah.
Okay. Sorry for that. Today's talk is entitled How to Program Your Quantum Computer. It is dedicated to quantum programming. But first, before programming actually on a quantum computer, on a simulator of a quantum computer, first we're going to have this little talk, this little lecture, however you want to call it, this discussion on the fundamentals of quantum computing theory. And let's begin from the basics, the 3 fundamental principles of quantum computing, which are quantum superposition, the wave interference, and the quantum entanglement. Together they create the computing power that can solve problems even exponentially faster than classical computers. And the first one is the quantum superposition. It is one of the most fundamental and one of the most well-known principles of quantum mechanics. A quantum particle can be excited and not excited at the same time. just like us when we started hearing about quantum computing for the first time. Or just like Schrodinger's cat, which was this whole thought experiment about a cat being in a box, being at the same time dead and alive. It was in a superposition. The spin, the position, and the energy of subatomic particles. The spin, the position, and the energy of subatomic particles can have more than one values at one time. Actually, they can have a linear combination of all these values. And this is the main reason behind almost every quantum computing quantum algorithm's effectiveness, since it allows quantum systems to see and manipulate a lot of different data simultaneously. The second principle, I'm sorry because I cannot see the presentation, but I hope everything is okay. Great. The second principle is that of interference. This is not something explicit to quantum systems, but it is the property of waves to interact constructively or deconstructively when they encounter one another. This is exploited in quantum computing in order to eliminate the possible outcomes of a superposition, to only get the ones that we need. And the third and last one of these fundamental principles of quantum computing is the quantum entanglement. This is the most important, but at the same time, the most weird, the most counterintuitive phenomenon about the quantum world. It is what Einstein described as spooky action at a distance. Two entangled qubits are described by the same wave function, so they share information. And when one of them is measured, the states of both of them collapse at one instant, even if they are separated by light years in space. Actually, what we see that they're doing is that they work as the same one entity as a whole. I cannot explain how this is done or why it is so, but I can guarantee that this happens, as it's backed up from many experiments and many attempts to be discarded. And it is required for almost every quantum computation that has an advantage over the classical analogues of them. I think the best way to talk and learn about such topics is only through practical experimentation. And that's exactly what we're going to do in the second part, after the break, during the workshop. So now that we know about these fundamental principles that render possible quantum computing, we can get into more interesting topics of quantum information. It would be helpful to first remember how classical computers work, where the basic unit of information is a binary digit, a bit. A system of only two possible states. It can be in the state 0 or in the state 1. And it is used to pass information through different classical systems. In just the same way, in quantum computing, we also define a basic unit of information called the quantum bit, or a qubit. Only the difference here is that this is a quantum system able to exist at the same time in the state 0 or in the state 1 or at any superposition of them. And by superposition, I mean a linear combination of state 0, state 1, weighted by some probability amplitude. But these probability amplitudes are some complex numbers. I don't know if everybody knows what the complex number is. It is a number that has two parts, a real part and an imaginary part. And when these probability amplitudes are square, they give the probability of measuring the qubit at the state they correspond to. We're gonna see how we can demonstrate and visualize all these qubits, because as somebody can imagine, it is a really complex system to visualize, since it has two numbers, as you can see here on the slide. I hope you see the slides. Great, thank you, Silja. You can see that there is the probability amplitude A and the probability amplitude B. I said both of them are complex numbers, so they compose of two number seeds, in total 4 numbers, so it would be really difficult to guess how we would visualize it in a 3-dimensional space. But we're talking about it in just a few minutes. Before that, let's talk about how we can harness the power of qubits. Yes. How we can harness the power of qubits. And for that purpose, we employ the quantum gates. They are the building blocks of quantum computation. Again, analogous to classical logic gates that I guess, if not all of us, many of us should be familiar with. And these operations interact with the quantum registers, allowing us to construct intricate quantum circuits, paving the way for complex computations and algorithms. I won't get into the mathematical details of the gates, but let me just mention that they are represented by some unitary matrices that are applied to the state vectors of the circuit. Nothing too complicated, with a little of linear algebra. I won't get practically. I'm sorry. What we achieve by applying a gate to a quantum circuit is to manipulate these probability amplitudes of all the states that exist in the circuit, in these different qubits of the circuit. And while doing so, we don't want to break the requirement that the sum of all these probabilities must be equal to 100%. 1%, that is, the square of all of these probability amplitudes must sum up to 1. Some of the operations we can make using simple gates are bringing a qubit into a superposition using the Hadamard gate, or entangling 2 qubits using the controlled knot gate. A lot of different gates. I'm not going to explain everything now. We're going to see them in the workshop and understand really better how they work and what they do. And that's all from my side for the theory, for the basic theory of quantum information. But let's go now to see a bit more of how we use these quantum computers, where we can use them, where we can see them, why we have them, and what different types of quantum computers exist. Now Orestes is going to talk. He was, as I introduced my team in the beginning, from my team, and I don't know if there's a problem or...
we have just a little technical issue, so if we can wait just a couple of minutes.
Yes.
For sure. I think that also I've been having some questions in the chat personally, and there's also
You can ask me.
I will. Oh, okay. Also, so the first one that I have is that if there are only 3 properties of quantum mechanics, that's the first one.
If there are 2 properties.
If there are only 3 properties of in quantum mechanics,
No, of course not. Quantum mechanics is a really complex theory, but what I talked about are the 3 basic principles that quantum computing is based on. And quantum computing is not, of course, the same as quantum mechanics, just like electromagnetism is not the same as classical computing. It's just the physics that we use.
Awesome.
Yes.
Awesome. And the other question was about the, I believe, wave-particle duality. So I have a question about how does this duality challenge or traditional understanding of particles?
How does this duality?
Yeah, challenge or traditional understanding of particles. So I can write it right here in the chat. I can put it like in the as well. So was this question. How does this wave particle?
Okay, I cannot see it in the chat, but I can answer it.
Yeah, here it is.
What is this duality, wave particle duality? How does it challenge our traditional understanding? Yeah, our traditional understanding before all this quantum theory was that particles were just some small balls throwing off inside empty space, inside the atoms or anything like that. But this just did not explain all the theories all the experiments that we saw, and a lot of experiments, like, for example, like the black body radiation or the photoelectric effect, and the wave particle duality is just just a new theory. It's actually the basis of quantum theory that allows us to explain and understand all these experiments, and of course think and construct the theory for quantum computers.
Awesome. And I think that I have the last one while we wait.
Yeah.
So how can I will write it, I will just copy paste it from the chat that I have. Okay, so here it is.
How can entanglement potentially be applied in quantum technologies such as quantum computing or quantum communication? That's also a really interesting question, because quantum entanglement is the basic principle of quantum communication. We can think that in some years in the future, a lot of years or not too many years, I'm not sure, we can imagine a society that shares pairs of entangled qubits, and this will mean that we won't have to send too many bits of information. For example, there's this principle of super dense coding that states that you communicate the information of 2 bits, the information of 2 bits, sending just 1 qubit if you have some entanglement, some pair of entangled qubits. So this is the direction on which they're going to help communication.
Awesome, great. I think that those are the questions so far that I have. So yeah, now we can continue.
Great, that's great. So is the rest is ready?
Okay.
Yes, I cannot hear you very well.
Okay, now there's some technical issues here, so with the Wi-Fi, so I hope everything is good.
Wait, I still cannot hear. I don't know, Elisa, do you hear him or is it my computer?
No, I cannot hear you. I cannot hear him really good. It's like, yeah, I cannot hear.
Okay, now can you hear me?
No. Maybe you can take the headphones of somebody else.
Yeah, perhaps that could be a solution.
Yes, I'm so sorry about that, but you know, it happens when you...
Yeah, it happens. So no worries at all.
Yeah, the guys, Joanna, Concetta, and the rest are in the university in order to help afterwards in the second part, to help the people that are there with the workshop to go and help with the code there. So
no worries, it happens. Perhaps in 10 years more with our computer, it will be solved.
Exactly, we hope so.
Yeah.
As engineers, we always find solutions for problems. So let's begin.
And
You can
problems
hear
for
me?
solutions.
Yeah. Let's begin. Mirrors, the slides.
Hello. Yes.
Okay, let's begin by talking about types from quantum computing. You may have heard that from Mirrors there are some basic quantum theories, but there are many ways to implement them in real life. First of them, there are superconducting quantum computers, which are the most common used quantum computer in our current industry, as well as research. These quantum computers are operational near absolute zero temperatures, so quite difficult to be scaled in large data sets or in a more easy access way. You may see them in this shape like a chandelier. The second and most newly researched quantum computer is photonic quantum computers. These quantum computers are gaining in trend in recent years because they don't require such extremely cold temperatures or extremely noisy-free environments to operate. The third one is the more researched one you may see is the ion-trapped quantum computer. This quantum computer uses very extremely powerful lasers to manipulate ion-trapped electromagnetic fields. So we are extremely difficult to operate them in a more common environments. Exceptions can be made in research labs, but are the most least error-prone quantum computer we have currently. You may ask me, how can we access a quantum computer? Currently, as our workshop told you so. There are many ways. The most common way is to access a quantum computer through the cloud computing, like IBM. You may gain access to like IBM. First of all, you write your code in your from your comfort of your home, and you can send your code freely to a quantum computer in order to access the quantum hardware. And when the code is ready to be executed from the quantum computer, it will be executed. You will get the quantum computer will send you back your results from your code. And after that, you may ask, okay, in a couple of years, 10 years, maybe, nobody really knows, we will have a future where quantum computers are used in our daily lives or help traditional hardware systems calculate difficult problems. First of all, most upcoming application is material or drug discovery. Quantum computers, they will help current algorithms in order to simulate better the quantum nature of atoms from which the molecules, atoms which from the molecules are constructed, and from molecules we construct materials like metals or drugs. This will help scientists to discover new exotic materials and drugs that can help our advance our civilization and also improve our daily livings. The second and most funded one for obvious reasons are financial modeling. Many algorithms needed for the risk management and portfolio manipulation are based on the large linear systems. In order there are some ways computers can help these linear systems to be solved faster and more efficiently. And the third one, and the more you have may heard, is cybersecurity and cryptography. Quantum computers can pose a great danger to society by breaking, using source algorithm, the current cryptographic system. But there are many solutions to that problem, and some of them are implementing already in some advanced applications. Using quantum-based algorithms or classical algorithms inspired by quantum computing, but the future cryptography will be quantum-based using quantum computers. This is the most current effect area in our society. So if you have any questions, please be free to ask them.
We will continue with questions at the end, but
Yes,
now
I have. I will gather some questions. So I have several questions for my personal in my personal chat, but I also see one in the common one. So we can, if you're comfortable with, I can ask those at the end. That sounds good. Okay.
Yeah,
awesome.
I think it's about sorting your scat and things. So maybe at the end it is better.
Awesome. I will gather those.
Great, great. So let's continue with it.
Hello, and from me. Can you hear me clearly?
Yes.
Okay, perfect. Okay, as you have realized and understand by now, the concepts and the mathematics of quantum computers are very, very complex thing. The applications that we are just presented are like they use multi-dimension of quantum information, entries, properties. You know, it's like almost impossible to understand and visualize. And for this exact reason, there have been developed ways of visualizing quantum states. In more detail, let's dive into this. First of all, we have the Bloch sphere. The Bloch sphere is a visual representation used in quantum computing to describe a single qubit. You can see it also in your screen right now. That's the visualization you see in your computer. The north pole of the sphere represents the quantum state 0, while the south pole represents the quantum state 1. Points on the surface of the sphere represents different superposition states where a qubit can exist in a combination of 0 and 1.
I'm sorry, you have to open your microphone. I'm so sorry. I muted. I wanted to mute some other person.
Why did you mute me?
I'm sorry.
Is this a beef or something beginning here, Miran? Okay. What did you hear last? Where did I left it?
I
It
think
was
that we
just for a
heard everyone.
second?
Yeah.
Okay,
Yeah.
perfect, perfect.
That's the good thing.
Okay. Okay, perfect. Okay, the angle around the sphere represents the face of the qubit states, okay? A quantum operation can be conceptualized as rotations on the sphere, okay? When we measure a qubit, the result corresponds to the projection of the vector onto the central axis of the sphere. The Bloch sphere provides an intuitive and visual way to understand the behavior of qubits in quantum systems. The only problem with the Bloch sphere, as you can see, is that we can only exhibit one single qubit. So, for this exact reason, the well-known IBM created the Q-sphere, which in the Q-sphere, we can represent multiple quantum states onto the sphere at the same time. This Bloch sphere, oh my God, this Q-sphere is particularly used for illustrating these multiple qubits simultaneously. It provides a clear and intuitive way to understand the complexity of quantum states. More specifically, I may dive into it a bit. In order to show all the superposed states, each state is represented by a point on the sphere, on the surface of the sphere, of the Q-sphere. You see, we all the time have the qubits on the surface, not inside the sphere. That's important to understand. It is also very useful to visualize the superposition and the entanglement of the qubits that are very basic quantum knowledge and positions, but it's not very easy to comprehend and understand. In the superposition states, a qubit exists in a combination of multiple stages, and these combinations are clearly shown in the Q-sphere. Also, in entanglement, where qubits become correlated and share information, it's also visually presented in the Q-sphere. States of the qubit are color-coded on the Q-sphere to help distinguish which states they're in. The different colors represent the phase of the qubit, and the different size of the points, like how big is the circle, represents the probability amplitude. Thank you.
Exactly, and I'm not sure if sometimes it was difficult to hear or
No, it was
maybe it is
awesome.
okay. Okay, because sometimes I just lost the sound. Maybe it was my problem. So let's continue with Joanna. And
Okay, so we saw the basic of quantum computing and also some tools we can use to build a quantum circuit, such as the quantum gates we saw before. Now, if we want to grasp a first idea of those tools and the properties in action, we can use a rather intuitive example of a quantum circuit, the quantum adder. We choose the adder circuit as it can be simply implemented and it involves the operation of addition with which we are all familiar, I hope. Starting from the classical adder, we observe that the addition happens digit by digit, sequentially calculating the result for each digit of the input. For example, in a binary adder, the addition happens from the least significant bit to the most significant one, and the carries are propagated to the more significant bits as the operation is taking place. Each bit that is being handled can only have two distinct values, either 0 or 1. Finally, we easily notice that if we introduce a certain input in the classical adder, we expect a certain output, the same each time, no matter how many times we repeat the operation. And this implies that the system of a classical adder is deterministic. When we get to the quantum adder, however, we observe some major differences in the mode of operation of the circuit. First of all, the system is no longer deterministic, but probabilistic, meaning that the qubits in the adder can not only exist at one state at a time, but also simultaneously in a combination of states at once, each with a certain probability. The probabilistic nature of the circuit is introduced through the two core principles of quantum computing we talked before, superposition and entanglement. Entanglement correlates pairs of qubits to perform the calculations of addition in a quantum adder, whereas superposition is the property that allows us to handle different qubit states at once during the addition. This enables the calculations to be applied in parallel for all combinations, which is the main factor of speed up in a quantum adder compared to its classical equivalent. Finally, another key difference we can observe in how the quantum circuits are built is their requirement for reversibility. In a quantum computing, each gate applied to a set of states should be reversible to allow us to retrieve the original state from the final one and thereby maintaining total information. This property dictates the need for an equal number of inputs and outputs in quantum circuits, and this is a restriction we do not need in the classical equivalents, where the information loss is a manageable phenomenon through various algorithms. So this is a brief comparison of the two others and offers a first idea of how the fundamental building of a simple quantum adder differentiates from a classical one. But now let's try to obtain an intuitive approach of how a quantum adder really operates. We consider the input of the adder to be a superposition of states, which are propagated into it. Inside the circuit, the operations happen in parallel, as we explained, meaning that each gate of the adder is applied to all linear combinations of the probability amplitudes at once and affect each one of them accordingly. This parallel procedure offers an even exponential speedup in computations and outputs a distribution of all possible states, each assigned with a different probability of being the sum of the addition we need. In order to obtain a single value as the sum of the addition as expected, we run the same operation multiple times, and we measure the result, thus collapsing the superposition of states. The repeated measurements provide a statistical distribution that converges to the correct result over multiple runs, And we repeat as many times as needed to obtain a result with statistical significance, finally acquiring a value that is in accordance with the classical adder out.
Exactly,
This
this
from me.
was the quantum circuit, and it was maybe not the simplest, but the most intuitive circuit to understand. The most, in our opinion, the best circuit to show us a first example for understanding how quantum circuits work and what are their differences compared to classical ones. But there are also a lot of different other algorithms, more complex and more interesting, more widely used, and of course more exciting. But we're not going to see all of them. We're not going to talk about the most famous of them, that is the source algorithm, is about quantum cryptography and code breaking of codes, cryptography. And the last algorithm that we're going to talk, I'm not going to analyze right now, but I hope we're going to have time to see it in the workshop, is the Grover's algorithm. It is a quantum search algorithm that is polynomially faster than the classical one. As both I and Joanna referred to before, quantum computers can be even exponentially faster, but this is not, the best algorithm that to do the comparison. Although it is a really good algorithm and a kind of intuitive to understand why it is so much faster, because in a classical computer, if we want to search some element of a big list that we don't know where it is, it's not an ordered list, we don't have hash keys or anything, is to search the whole list until we find this the correct number. This has a time complexity of n. This means that when we have a list of n elements, we have to run this algorithm to search about 10 times, maybe n divided by 2, but it is not, it doesn't make a difference. On the other side, in this quantum algorithm, this Grover algorithm, we only need to run the circuit one time. We run it through the whole list and we get the output. We get some output actually, because in this first time that we run it, we have a comparably not too high probability of getting the correct output, maybe around 40, 50%, maybe less, maybe more, depending on the length of the list. But we have to run it again and again, so we get more and more probability of getting the right output. And in general, we have to run it if we have a list of length n, we have to run it about the square root of n. So if we have a 9 elements list, we have to run it 3 times. And in this way, we have achieved getting with almost certainty more than 95% or something, with probability more than 95% the correct outcome, and running it polynomially less times than the classical ones. This is what we're going to see in the workshop later. As I mentioned before, we are going to have a break now after some questions that we can get, and stay here after a break, because in my opinion it is the most beautiful, the most interesting part of quantum computing. Quantum programming is, something different than anything else you have done. It is a new way of coding, a new way of programming. It is a new way of thinking, maybe. It is something really, really interesting. So take a break. I'm taking the questions, then you can take a break, and then we can go.
For sure. So thank you so much for this amazing presentation. I was like so happy to hear from all of you. But I've also been having like filled with many questions right here. So I will try to ask them, like the most of them possibly. So yeah,
I'm sorry,
I'll go.
before
Yeah.
asking the questions, I said that I'm going to share my information so everybody can contact me or my team. I put here on the slide my LinkedIn link URL, and because I did it on really the last time, I didn't get information for the rest of my team, but you can, all of you, Anna, Concetta, Resti, you can write it in the chat. So whatever you want to share, and everybody is going to see it. And I'm ready for the question. Sorry to interrupt you.
No, for sure. I think that's really important so that we can have all of the social media and to be connected to LinkedIn. I think it's such a good platform to connect. So that'll be great. And do you want me to wait until everyone puts like their social media, or I can like just go straight to the questions?
You can go on and ask the question because it is done asynchronously. I guess they are writing, so.
Okay, awesome. So the first question that I have first in the chat is about hello from Mexico. So we were wondering how many qubits does a quantum computer needs to have? Oh, to have a powerful computational. No, I believe that it would be like a computational power, a higher computational power. So I'll put it in the chat for you, but I think they
higher
mean
computational power.
yes.
Compared to the classical ones, or?
Yeah, I think so.
Mm-hmm.
So this is the question.
Hello from Mexico. Hello. Great. How many qubits we need? To be honest, I'm not sure right now from my mind to tell you how many we would have, or if we would be able to have more computational power. But it was a circuit to demonstrate that how quantum algorithms work, because as Joanna said, they make all the calculations at the same time, not in parallel, but in a superposition of all these states.
Exactly. Yeah,
it's
and
really
also
something I haven't thought about the. I'm so sorry about the power, the computational power. Maybe Joanna, if you have some idea, since you talked about it, but if not, I think.
yeah.
If you can send me, I'm going to search for it. I'm so
Joanna is
sorry.
having a technical problem, so yes, but as she thinks she doesn't have like anything else to add.
No
Great,
worries,
so
no worries.
you can contact me, and I will be sure to search about it. And
yeah, definitely. I think you can contact Maren as well. What I only know is that, for example, IBM has been launching sort of different right now, adding more qubits, and there's actually a startup that recently launched also this year, just for you to know, the first like 1,000 qubit quantum computer. So I think that I'm not an expert in the area, but I know that it's an improvement from what we have known for the qubits. So yeah, just for you to know, I put the name here, Atom Computing. They launched this year the 1,000 qubit computer. So if you want to learn more afterwards. So yeah, I'll go to the next question. So I think that it was actually here in the chat also. So a Schrodinger cat can exist in two different states simultaneously when unobserved. Does this phenomenon introduce uncertainty in the functionality of quantum computers, and how is precision achieved?
I'm sorry again. Is it in the comments?
Yeah, exactly.
Okay, I'm so sorry because I hear some.
No worries. It's in the chat. I will be putting all the questions.
Schrodinger's cat. Yeah, okay. Can exist in two different states simultaneously. Does this phenomenon introduce uncertainty in the functionality of quantum computers? Yeah, of course. Quantum computers are some not deterministic but probabilistic systems. Actually, all quantum systems. This is what we exploit in order to get better and faster algorithms and computation.
Should I
Yeah.
go with the other one?
Wait, because does this phenomenon introduce uncertainty? Yeah, it does introduce uncertainty, but in the functionality and how is persistent? How is persistent? Okay, yeah, this is a really good question. We're also going to see this in the workshop. For example, using Grover's algorithm, because in Grover's algorithm you can see in the beginning, before adding the whole circuit, we have a superposition of many different states. And we add a circuit, and at the end we get only one with a really high probability, only one and the correct output that we want. So this is how the precision is achieved.
Exactly.
I don't know if I explained it well or not. Maybe you can ask again if you have some follow-up.
Awesome, and yes, the uncertainty is the fun of it. I totally agree with it.
Exactly.
I also have a few other questions right here, so I will try to make it short because we have a lot of questions right here, but I know that we'll also have like the scheduled break. So
Yes.
How do we run? So I will actually paste it again in the chat. So there's a question about how do we run problems or simulate them in our quantum computer. You already explained the circuits and algorithm, but would it be possible to explain a short step-by-step to do that? Okay.
Yeah, it is possible, and I'm going to do it after the break. It is what the workshop is about. We're going to run some circuits in a simulation of a quantum computer. I'm not going to explain it now, but we're going to have a hands-on workshop exactly on that, so don't worry.
Exactly. No, I was going to we don't need to spoil it. That's right. And I think that the last question would be, so here I have one, how can the quantum adder circuit can be faster than the classical one? So it's already in the chat as well.
Yes, I think that's what we answered before, you know.
Okay. Okay. And then
yeah, I said that you can contact me and I will be sure to search and answer about it. I don't think, no, never mind.
Okay, awesome. So great. So I think that we have those questions so far answered. And if anyone wants to like keep asking the question, please send it to me personally if you want, so we don't interrupt the meeting. But so far, I think that we have the scheduled break. So anyone can just take a break, relax, and come back in, I believe, 10-15 minutes. Yeah.
Yes, so let me stop the share screen and see what time it is. It is 7:15. So let's do it at 7:30. 7. It is at what time it is, and 25 minutes, something like that.
Okay.
Let's.
Okay. Great. Awesome. So
I'm going to leave the meeting and enter again because I have to.
Awesome. So just to be clear, in 50 more minutes.
15. Yeah.
15 minutes. Okay, so great. So see you everyone in 15 minutes. Take a break and we'll see you.
Great. So let me share my screen and begin. At least people from Patras should have received it with by mail. So they should be able to find it.
So everyone try to connect with that link that is provided in the chat, so we can join the link and see exactly the same in your screen about what Myron is presenting.
Exactly. Open this link. This should open. I'm so sorry. Maybe I should have sent it before the break, but no, because break is not to work. It's to relax and get ready to write some code. So this should open to everybody. If somebody has a problem, please share it with me. You can write in chat, or you can raise your hand and virtually via Zoom. So yes, it is in the Zoom meeting. And it should ask you if you trust the person that wrote it. I wrote it, you can trust me. It's not from Google, but you have to click it in order to continue. And please tell me if you can see my screen. Ah, wait. No. Now you can see my screen. Great. And then you can either go from File and where is it? Save a copy in Drive, and you can save it in your Drive. Or you can go on any block of code and press Ctrl+S, and it will ask you to save a copy in your Drive. As I said in the invitation for the event, you don't have to install anything in your computer. Everything is on cloud. This is Google Colab, and it is running Python through a Jupyter notebook. It is the Colab notebook of Google. So let's first of all run the first block of code. It is just some pip installs to install the libraries in the machine.
Awesome. I encourage everyone as well, just to repeat what you said, Myron, to create the copy then, and also just to remind you that this will be also uploaded to YouTube afterwards. So don't worry if you miss something. You can also try that at your home to try to code this. The same things will be in YouTube, so no worries about that as well.
Exactly. You will upload the video. You will send it to us, right? So we will also share it or use it anyhow. And the workshop is going to be on our Drive on the same link that I sent for as long as we have it. I don't know how long, but not a few days. So if everybody has run this first block of code, it was just some pip installs. You should be familiar with it if you have used Python before, Python libraries. We will use the kke library. That is a library developed by IBM. It is a simulator of quantum computers, and it's actually a quantum computing language developed by IBM. The kke IR, we are going to use it. It is a simulator developed again by IBM. And I'm going to give you 1 minute now. If anybody has some errors, either someone that is watching from home, someone from the classroom here in Greece, or in Chile, or in US, in Mexico, I don't know where else, in India. Anybody who has some problem, you can say it now in the next minute.
Yeah, that's a good thing. That also just to, if someone is listening to this afterwards from YouTube, we've had some people from the Girls in Quantum team from different parts of the world that are joining. So happy about that, about having different classrooms, from people learning. So I actually have received many questions from them, especially from the Girls in Quantum in Mexico. So I'm so happy about that. And yeah, feel free to ask any questions. We know that sometimes it might be difficult to connect, or perhaps if you have a technical question, so let me know that as soon as possible, so I can also mention that to Myron.
Exactly. And thank you for saying all this, because now the meeting has passed. So I guess that everybody has run the code successfully. By the way, we ran with shift plus enter. If you had this question, I hope you don't have it now. And either we're writing here and shift plus enter, or by this little icon here on the left. Then we need to import the libraries. We're going to import from kke library the quantum register and classical register. We're going to see where we use it, the quantum circuit, and some simulators and some methods to run the simulators and get the results. And from kke visualization, we're going to plot the block sphere. I'm so sorry, and plot some histograms, the state, the Q sphere, and the state sphere, the state city. And from math, NumPy, this is not so important. It's just for some calculations. So let's begin with the basics, just like in the theoretical presentation, the theoretical discussion we had before. First of all, we need to define a circuit. We define it in this way. We define some size. I said the size is going to be 2 for now. And we define a quantum register in the variable QR and a classical register. The classical register is going to be used only after the measurement of the whole circuit, of the whole quantum register. So they have to have the same size in order to get the calculated outcomes in the classical register. We have some superposition in whatever calculation we're doing in the quantum register. And once we measure the register, these superpositions collapse into some classical bits that we can store in this classical register. And the quantum circuit is the combination of these two registers. It is a hybrid, you know. It has both classical and the quantum register. If we run this, we can use this QC. QC is the quantum circuit. It's usually how we denote it in only 2 letters in, you know, fast way, because we're going to use it a lot. And we can draw the circuit using the MPL parameter, which stands for matplotlib. This is a library of Python again that is used in many situations. Nothing have to do with quantum computing, but we also use it here in order to visualize it more elegantly, more beautifully. If I take it out, we can visualize it using text, and this is the 2 qubits that we have and the classical bits. So I was going to show you all without any gates to see how it is initialized in a state of everything 0, but since it is already after half past, I'm going to skip this part and just add some gates here and see what happens and how we are going to get some results. The quantum gates that I talked about before, as I talked about before, are these operations that will be applied on the qubits to change their states. And we're going to play now with only 4 of them. The 4 most basic and most common ones. The X gate, which applies the NOT operation. It is really, really similar to the classical NOT operation. But it has a difference that it has to do with probabilities. So it just interchanges, it transposes the probabilities of finding the qubit in the state 0 and in the state 1. So if it is 50-50, nothing is going to change. If it is 30-70, it is going to be then 70-30. We're going to see it in practice. So let's put in the quantum circuit that we have to add .x. We use the method x. It is really, really easy to apply the X gate. And here the parameters that we have is the qubit and some labels and some others, but the qubit is the important one. So let's put it to the qubit number 0. The qubit number 0 is the first qubit, the rightmost qubit, if we see it like a vector. And let's run it and see what happens. Here you see it is just a square, a gate that is applied here. Then we have the Z gate that changes the sign of the amplitude only when the qubit is in the state of 1. So when it is in the state 0, nothing changes. Let's put it again here to see what happens. QC.Z. It is again just as easy to apply any gate. And here we will run
just
it.
to
Yes.
Sorry to interrupt. Just to clarify, I have some questions in the chat, but just to quickly remind someone that if you apply, for example, if you have the 0 and you apply the X gate, you'll turn it into the other one, so 1. So just to clarify that, I saw some questions in the chat about like the 0s and 1. So when you apply the X, if you're in 0, it will be 1, and if you're 1, it will turn on in 0. So yeah, just to other reminders. Sorry to interrupt.
Exactly. No, it was very good that you mentioned that, because I think maybe I was going too fast or I was explaining it too complicatedly.
No,
So
no worries. It was good. It was good. Just to let everyone know.
okay. Let's apply just the X gate that we learned about, and let's see how to visualize them. Here we have the simulator. It is the IR simulator that I talked about, we imported, and specifically the state vector simulator. This just gets the state vector is the vector with all the states that exist in the circuit. We have to execute the job for this quantum circuit that we have QC with this simulator for some shots. Here we do not measure anything, we just get a theoretical approximation. So we just get one shot, and we get the result, and from the result we get the state vector. And we can draw it using LaTeX, not sure how to. And we get here this state, 0 and 1, because the qubits are initially always initialized to everything 0. So now we applied an X gate in the on the circuit indexed 0. So it is the rightmost, and the rightmost gets N1 here. So now let's go on and apply a QC.Z gate, again to the same qubit, the 0th one, if you want. And actually, let's apply it to both of them, QC.Z, to the first qubit. So here you see we have this first qubit in the state 1, and we apply Z, the second qubit in the state 0, and we apply Z. And what's going to happen? As I said, here it changes the sign of the amplitude of only the qubit that is in the state 1. So this qubit's state is going to change into minus, and this state is going to stay positive. So the total is a minus state. But let's not think about that. We can go on and see about the Hadamard gate. That is a very interesting gate. It is the gate of superposition. It is the gate that superposes the qubit into two states at the same time with probability of 1/2 and 1/2. So as we said, since the probability is the square of the probability amplitude, the amplitude that this gate applies to the circuit is 1/√2, but we're not gonna see the mathematics here, just apply the gates. So QC.H for Hadamard, again, totally easy. In the second qubit, the qubit number 1, it was in the state 0. So now we're going to get a superposition of it in the state. Let's delete this. Now we're going to get a state of a superposition of the left qubit in 0 and 1 with probability 1/2. So the right qubit is 100% of times in the state 0, here and here as well. But the left qubit is with 1/2 probability in the state 1 and with 1/2 probability in the state 0. 1/2 is the square of this number here. And then the final gate that we're going to see in our examples here in just a few minutes is the CX gate. And this is the controlled X gate, the controlled NOT. This is the only gate that we see that applies to 2 qubits. And it has a target qubit and a control qubit. So depending on the control qubit, if it is on the state 0 or on the state 1, it applies or does not apply an X gate on the target qubit. So let's see it here. We get first the control qubit, you can see it here, and then the target qubit. So let's say that control is the qubit number 0, target is the qubit number 1, and here we can run it. And before seeing the results, we can think what the results should be. Initializing the circuit, both of these qubits are in the state 0. So then the control qubit is 100% with 100% probability in the state 0. So this should not apply anything, right? It should end in the same state of 0, 0, and it is true. But if we add here qc.x to the control qubit, that is the first qubit, the qubit number 0, you can see here this qubit. You can see my mouse, right, or not? Okay, great. So you can see this qubit is in the state 1. So then the control NOT gate is going to be applied. So this is going to apply on the Q1 a NOT gate, and we're going to get 1 and 1. So here it is this outcome. I hope it is clear, both from a view that it is big enough to see, and from understanding that you understand why we get this outcome.
Yeah, no, for sure. I think that it was so great, and I have a few questions on the chat also. I'll tell you just one or two in regard of this, and that would be great. But I think it's so great to see this. I honestly, personally, I saw this like 2 years ago, like in one of the first classes, and this sort of session reminded me a lot of things that I forgot. So that was so good for me as well. Yeah, so I have some questions here in the chat, so I'll put them right there.
You can ask me because
yeah. So when the Hadamard gate is applied followed by a phase gate, or vice versa, what is the resulting effect on a qubit state, and in what quantum algorithms or protocols are such combinations particularly useful?
Yeah, because I think we're getting a bit too late, because maybe it was my fault. I have too many things to show, but we're going to apply Hadamard and the Z gate, Hadamard and X, Hadamard and controlled NOT, all of these combinations. So you're going to see it in practice. Maybe I should get it a bit faster, given that everybody understands so far what's going on. So let's stay with this state, 1, 1. Actually, no, let's get a more interesting state. Let's get an X to 0 and the Hadamard to the 1, to the qubit number 1. So here we should get a combination of 2 states, a superposition, since we applied the Hadamard gate, and indeed we get 0, 1 and 1, 1. So now we have gotten the state vector from here, from the simulator, and we can go on and plot the Bloch spheres. It is the Bloch multivector. Why multivector? Because it is multiple Bloch spheres, since they are corresponding one to each one of the qubits. Here we have 2 qubits, so we're going to get 2 Bloch spheres. And let's see what these spheres look like.
Awesome.
For the qubit 0, it is in the state 1 with 100%, right? When Concetta talked before, she said that the probability of the state is the projection of the vector on the main axis, and here the whole vector is on the main axis, so it is with 100% probability the state 1. The second qubit, you can see its projection. It is in the horizontal plane of the equator, so the projection onto the main axis is going to be exactly in the middle between 0 and 1, so the probability is going to be 1/2. I hope it is not too difficult to understand, and then we can go on and plot some of the Q sphere. Here it is like that, the 0, 1 state and the 1, 1 state. If we want to get something more interesting, as you said before with the comment, we can go on the circuit here, and instead of this, change you can write as I go, or you can write your own circuits. It doesn't have anything to do. You can experimentize while I talk and I explain the circuits I think about. You can write your own circuits and experimentize with them. Now, let me show you this. If we apply the Hadamard gate here, and then the QC, on QC, we apply the Z gate, as you said in the comment, we're going to get this result. And here you can see that we change the phase. Okay, it is 180 degrees rotation of the phase. So here, the 180 is going to be not from this side, but from the other side in the Q sphere, because it rotates 180 degrees. Yeah, I changed the first and the second qubit. Here, you remember it was from the front side, now it is from the back side. Nothing too interesting, but here you can see the phase, it is 0, it is going to go to pi. So it should be yellow, not both of them, but only the second, because the state 0, 0 is in the state, it has a plus sign. The state 0, 1 has a minus sign. It has a rotation of pi radians. So let's see if we get it right. And indeed, the state 0 is yellow now. The state 0, 1 is still has a phase of 0. And finally, before going into a little game I have prepared for you, let's see how we make the measurements in these quantum circuits. I'm sorry, I have to put my battery in the
Oh, of course. And also, while you're doing that, I just want to remind everyone that if you also have some questions, you can also email us. So I will afterwards, after the webinar, I will put our email as well, and the Myron's email as well, perhaps.
Yes.
Yeah.
Yes.
Awesome.
Do please do.
Awesome, and I'll do that. And you can email us, and we can also provide us as Girls in Quantum as well some resources as well. So Qiskit has amazing resources as well, so you can like go ahead and experiment. This is so great. As Myron said, the great thing with this sort of workshops is that you can plug as many sort of digits as you want, as many numbers and gates as well. So the good thing is that you can experiment, discover, have fun. So yeah, it's really, really fun to do.
Yes, exactly. And Qiskit is a great site for everybody that wants to start on quantum computing. Although I think now it is changed from qiskit.org, whatever it was, to quantum.ibm.something. And a lot of pages may not open from my experience in the last few days. But it's going to get fixed soon, so not too many words about that.
Awesome. I have shared the resource right there, so if anyone wants to take it out.
Great. So now we measure the qubits. Again, I wanted to say so many things about that, but we just apply this measurement from the quantum register to the classical register. I said in the beginning that we get the quantum register and measure it and store it in the classical register. Then I will draw this the circuit using MPL again. Display is just a function of Jupyter notebooks to display anything you want, some circuits, some images, anything. And then we get again a simulator, this time a different simulator. This time we get this QASM simulator, which stands for a quantum assembly language simulator. So this simulator changes this Qiskit language, this Qiskit libraries language into quantum assembly language and runs it. And since we have put here the measurement, we have to run it many times in order to get some statistically significant outcomes. I ran it for 100,000 times. Each time I get this simulator to this circuit and I get the result and get the counts. So what we counted. And then I plot the histogram, just like here we plotted the the state Q sphere. Here we plot the Bloch-Mult vector. It is just the same here. We do this and we get 50-50, almost 50-50 of these two outcomes. You can see here that even though here we have a phase, in the measurements, we don't have a way to represent the phase because we don't have complex numbers, just real ones. So it collapses along with the superposition and we get some real outputs that we can store. This here is the sign of measurement in Qiskit circuits, and we store this in the classical register. So now enough with the introductory things, and let's go play a game, a more interactive game. I have written here this get states function that is nothing. You can just run it. I hope it runs. Yeah, it runs well. It is just to visualize some things in the following examples. And I again have here a cheat sheet for the gates that we're going to use. X gate does the not operation. Z gate changes the phase, the sign of the state one. Hadamard H gate is the superposition gate. CX, controlled X, is the entanglement gate. I didn't say it before, but I have it somewhere upper. And it is the gate of entanglement. It entangles two qubits. We're gonna see how. And the multiple controlled X is just a control X with multiple qubits, 2 or more as control qubits. And let's go on and see our examples, our exercises, actually. We begin, let's first of all run these exercises. We initialize this circuit in the state of 0. It has only 1 qubit. And we want from the state 0 to get 0 minus 1. Of course, here and in the following examples, I only have the signs of the states, the signs of the probability amplitudes. I didn't write the whole states because it would get a bit too complicated, maybe for people not familiar with quantum computing, they would be confused by them. So here I have state 0 minus the state of 1. You can think about it and add your gates here and run to see if you get it right. Here, the amplitudes should sum up, the square of the amplitudes should thus sum up to 1. So it would be 1 over square root of 2 here and minus 1 over square root of 2 here. And what do we think about now? Adding some gates to get a different state of this circuit. The first thing that comes to my mind would be that we begin having just one state, having just a state 0 with probability 100%. But at the end, we want to get this superposition of 0 and 1. This is a linear combination, a superposition. So we said, we can say in the cheat sheet, the superposition, the gate for superposition is the Hadamard. So let's go on and put here dot Hadamard to the qubit 0, since we have only one qubit, the qubit 0. And here, if we run it, I'm sorry, I'm so sorry. It's not the QC, it's Q1, because we have defined this here for the first example as a variable Q1. So we run it here, and we get the outcome 0 plus 1. This is not what we want, though. We have 0 minus 1. And how we're going to use it? I would love to let you think about it and let you experimentize and see how it works, what would happen. But since we don't have enough time again, I'm going to go on and write it down. In the Q1, we're going to add the Z gate that adds the minus sign only when the state is 1. So here that the state is 1, it's going to add the minus sign. But in the state 0, it's not going to add anything. So let's get this, and we are finished with this as well. Now we took the correct outcome, and I think it was a pretty simple, pretty understandable example for a first time. And let's go on with the second one. Here, we again can run it and get nothing as an outcome. We haven't applied any gates. We get 0, 0 as an outcome. What do we observe here? The first thing that we observe is that we have 4 different states, a superposition of 4 states. So we should apply a Hadamard gate or more than one, because its Hadamard gate gives you 2 different outcomes for one state, 50% of one and 50% of the other. Here we have 4 different outcomes. We can say that the left qubit is in these 2 0 and in these 2 1. So it has 50-50% probability. The right qubit is again 0 half of the times and 1 half of the times. So I would go on and add in the Q2, now it is a different circuit, the Q2 circuit, we will add the Hadamard gate in 0, and then in Q2 again, a Hadamard gate in the qubit 1. This will run great and give us the result, but we can run it even better if we put it just like that, just like a list. This list here means that apply the Hadamard gate to all these qubits, the qubit 0 and the qubit 1. It's going to give us the same result. And the only problem we have now is that we have this minus sign here and here. And how we're going to get it? The only way that we have seen so far is to apply a Z gate. So we can go on and apply a Z gate. But where should we apply it? Here it is very easy. We can apply it either to the first qubit or to the second qubit. But here, both of the qubits are 0. It would be really difficult to think how we can apply some Z gate to that and get a minus, since nothing will change. But this exercise has a solution. It is not too complicated. You can experimentize or think about it. Since we are,
I think
yes.
yeah, sorry to interrupt, but I think Concetta mentioned that just a bit slower the step, please.
Oh, okay.
Yeah.
Yeah, okay.
Just as possible, because we know that we're in time. So yeah. Yeah.
I'm going to do it a bit slower. Also, if we don't have the time to do everything now, you will see, you will have it later, and you can see here the quantum adder circuit and here the Grover algorithm circuit. So you can run them and you can see the results. But even if we don't have the time to write some code now, we're definitely going to run them and just see the result. It's so beautiful. It's it was what I saw the first times I was getting into quantum computing, and it was what intrigued me to get a bit more to know about it and get into that. So I hope Concetta is all right now, and we can continue in a slower pace.
I'll let you know as well if any other chat, but I think that what you mentioned is great. And also, just to repeat, I know that I'm repeating this a lot of time, but this will be also uploaded into YouTube. So anyone that will be missing any steps, don't worry about that. I've been also receiving a couple of questions about different games, if there are like other games as well, and I will share about one that is the quantum test, which is also really interesting. So yeah, I'll let Myron finish, but there are really great opportunities as well.
Yeah, you can share all these ideas shared with us as well, and we also I had developed for my team some other games that we played, some other interesting programs that I can also share with anyone that asks for them. I don't have them ready right now. I have them in different parts of my computer and my cloud. It's a chaos. So if you ask me for them, I will send them. And here we can apply a Z gate. And where? I don't know where, but let's experimentize. Let's apply it in the qubit 0. And we get here. Here you see that the qubit 0 is down, the qubit 1 is up, not like the previous ones, because I have used here in KeyStDraw the parameter reverse bits. Because for me it is easier. I usually see from up to bottom and left to right. So the qubit 1 is the left and the qubit 0 is the right. So for me it's more intuitive in this way. Anybody can use or not use this parameter in their circuits. So if we apply this Z gate, now we get some interesting outcomes. We get minus in this state and in this state, but we want it in this state. So maybe what if we apply an X gate and change this qubit from 1 to 0? Then we're going to get a 0, 0 that has a minus sign in front of it, right? Let's see how we can do it. It is Q2. And we can apply a next gate to qubit 0, right? Because it was the right qubit. So indeed, here we got 0, 0 with a minus sign. And here we also have this minus instead of that, because it also changed. So now what can we do? We can think about it and see that these two states have the first, the left qubit in the state 0, while these two have it in the state 1. So we can apply a minus sign in these two and change. This will be a plus and this will be a minus. So how are we going to use it? Using just a Z gate in the left qubit. So we're going to add here Q2.Z. The left qubit is the qubit number 1, and we can run it. And indeed, this is the outcome that we get. So I hope everybody has followed the steps or did some other steps. Of course, if you put it in this way, first the Z's, then the X, or the Z's can also be in this list format, just like in the Hadamard. And it's going to be really more smaller code with the same outcome. And we just saved one line, actually. It's not that smaller, but yeah. And hope everything is okay in everybody that runs this in their computers, their drives. And let's go to the third.
I think it's so great so far. I haven't received any questions or concerns, so that's great. So you can go ahead and afterwards we can finish.
Great. We can finish how much? Okay. Okay, I'm going to go on and whenever you tell me, we can wrap it up. But here, this third circuit is, this third exercise is a really interesting one. It is, as you can see, this state here, it is the state of entanglement. Do you remember what entanglement is? It is a state of two qubits that are described from the same equation. And once you know one of them, at the same time, once you measure one of them, at the same time, you know both of them. So here we can see that if we measure this left qubit and we get it in state 0, we can see that definitely the second qubit is going also to be in the state 0. And the same with the state 1. If we measure any of them and we find that it is in the state 1, we will definitely, with 100% probability, at that time, without waiting any time, know that the other qubit is also going to be at the state 1. And here the circuit for quantum entanglement is in Q3. We have to first bring it in a superposition of two states, because we have one state and we want to get two states. So let's apply Hadamard gate to any of them. Let's apply it. Let's apply it to the first qubit. And then we can apply some other gate. What gate now? We want to change the second qubit here, the left qubit, not in this state, but only this state, only when the right qubit is 1. So only when the right qubit is 1, it means that the right qubit controls if we apply or if we don't apply this NOT gate, and thus it is a controlled X gate with control in the qubit 0 and target the qubit 1. And indeed, we get it here. And this is a very common, used many times in quantum algorithms for entanglement of, it is the circuit of entanglement. I'm so sorry. The fourth example is a really interesting one. I'm not going to run it now since we don't have enough time. I'm sorry for that, but you can run it on your machines, on your drives, and see how the results would be.
That's right.
Yeah, and
yeah,
this is actually the it was an intro into the quantum adder, which is going to be like that. Then here, okay, let me just get it ready and just add the solution to it. And you can then just find it and think about it, solve it in your own time. And for whatever else you need, you can contact me. Wait a minute. We can come here and just put it like that. And
so that way we can have like the solutions and everyone can like, oh, what's the solution for this one? So you can have it right there and also try and test it by your own. But I think
exactly.
Yeah.
And
awesome.
Do we have, I don't know, you want to close, or we have
like, I will wrap up now the session. So
okay, we have like just 2 more minutes for the last algorithm. I'm not going to run anything. It is already run here. Yeah, you see, it was too big for this workshop, but it is just the probabilities of the Grover algorithm. We get here this in the first iteration with almost 50% probability, the correct state that we want. You get here the size of the ball in the Q sphere. It is bigger than the rest, and the Q spheres. Then the probability gets to 90%. This size of the ball gets really bigger. Here it's 96% in the third time, and it is really clear that this is the correct solution, and in 96% of the times we're going to get it right using the Grover's algorithm. I'm so sorry I didn't I wasn't able to run it, and I think that's all.
No worries at all. I think that it was more than great, and I'm honestly so happy that we could host this session. I know that many of you have many things to do, so we'll wrap up right now. But thank you so much, Myra, for this wonderful workshop and all of your team because of the wonderful presentation before on how to program your quantum computer. I will now wrap this session. I'm honestly like so excited and so happy this was possible. As I mentioned at the beginning, we've been planning this, and Myra's team have been planning this a lot also in terms of the slides as well, the presentation and content. It's really difficult sometimes to share everything. So happy about that. And I'll now share, if you're able to share with me being host. I'll share a little presentation, a small presentation right now, just if possible. So yeah, so you can now see a little bit about the future as well of quantum, but really briefly. So yeah, please let me know if you're able to see this.
Not yet. Okay, now I think we can see it.
Okay, awesome. So it's mainly about the future of quantum. So okay, so I'm going to move you right here. So the future of quantum, especially as you've been seeing right now, many things that Myron mentioned and his team on quantum computing, on the theory, on what you can do, how to program, but also I wanted to mention about the future, what comes next. So it's really exciting, as I mentioned before, that there's like a record-breaking for this quantum computer, and that reached like more than 1,000 qubits. I think that scientifically this won't change much in terms of the computational power. However, it's much more than what we had in the past. And also, like, these small strategies for sort of investment in different countries. Just a small sort of data is that the Pentagon in the United States seeks to invest $75 million for quantum technologies, which is really small in comparison to what the state or the nation, the nation wants. So I want to tell you about the global landscape really briefly. I know that we're on time. So for example, right now different countries are implementing these different sort of national strategies, which is great for them to just start sort of investing in different research and development strategies, looking for clubs or perhaps people that are in this area so they can sort of foster that research. So Great Britain right now seeks to create a quantum-enabled economy. The United States as well aims to ensure this continued leadership in quantum information science. So actually there is the Quantum Chicago Exchange right there in Chicago. There's also IBM in New York. They have different centers as well, and all around the country for different quantum computers, which is great, especially to run different algorithms. Actually, as Myron was having this workshop, I was thinking, well, you can also access this quantum computer by yourself right now. So you can access IBM Quantum, and this is great because many people think, oh, we only need to have a real quantum computer in our house or at our home. But hey, you can access it right now, IBM Quantum, and you can find the quantum computer. So actually, here's like the great data. I will move you right here, right back because of the numbers. But we have here great data and statistics of countries, different countries sort of having these national strategies and sort of investing. For example, China is going to invest more than $10 billion in quantum computing sort of initiatives. They're actually right now have one of the best hubs for quantum computing to sort of do research once again, have more people, universities that are joining different partnerships across the world. And it's great to see that. And hopefully we can see more places, especially as I live here in South America, we can see also places having this sort of budget for quantum technologies. I want this presentation just to be briefed in general, and some of the things that I really want to mention to you is the 5 main things that right now these national strategies are focusing on. So as I mentioned before, priority research areas, so quantum algorithms, quantum machine learning. Also, many people are interested. I'm not really familiar with the concept, but quantum computing and perhaps the intersection with artificial intelligence. I'm honestly not sure how that works, but I think that it could be really interesting to look further into that. And the second thing is the human capital and talent, that I will go further with that. The research and development ecosystem and infrastructure, as I mentioned before, there are different now buildings and institutes that are working on that. In Germany, for example, Max Planck Institute right there is doing a great work. Perimeter Institute in Canada also. And I want to focus on this one specifically, human capital and talent. So right now, we had the opportunity to talk with Myron and his team as well, IEEE Patras, which is great because we can see that many people are getting interested in this area. And that is one of the main focuses that people or sort of companies now have, is to recruit people with talent that can sort of contribute to their companies, to their enterprises with their knowledge and their skills, because that's great. That's what if we have all the resources, but we don't have the people or the talent? So that's one of the key things that's why I wanted to do this presentation, to encourage you to be able to participate in these technologies. There are different case studies that are right now going on. So you can see like real life examples. For example, just a really short example, not going much into details. Mercedes-Benz is working with IBM Quantum to sort of simulate different molecules and chemical reactions in their quantum computer, so they can create better electrical batteries for their electric vehicles. And they envision themselves to be carbon neutral by 2029. So it's a great goal that they want to accomplish, and they are doing that with IBM Quantum. So they're so great. You can also explore these different sort of cases through IBM Quantum, and it's so great. They have like these videos right here that I'm not going to show you right now, but this is so great, especially for you to understand and experiment and see how this works, more than okay the theory, but also what can you do afterwards or in the real applications. It's so cool. As Myron said, he was like so interested in this, and that was like, if I'm not wrong, Myron, you got into quantum computing thanks to like that curiosity. So that's so great. And yeah, so we've been doing different projects for the same purpose, to sort of encourage more students. We've been creating a quantum geopolitics book, which reached more than 10,000 sort of impressions per people. We organized a quantum fall fest with θηκε and IBM, which was great as well, in a game that now is being launched in CERN in Switzerland, thanks to a great collaboration. So we're so happy about that. You can reach us out for any collaboration, and we also now invite you. I think that's the main, as I said before, the reason of this workshop as well, is to get you encouraged and motivated to participate in this field. There are many areas that you can explore, being a researcher, being in physics, being quantum machine learning, many different areas that you can be involved in, all of these opportunities as well. So I invite you to look at what's happening right now. There are many internships. For example, here I gathered with my team different resources from Google Quantum and Google NAI. So they have been launching these internships for people to join. Also Quantum Chicago Exchange, as I mentioned before, for your research, for being a PhD or just as a student, and also here for undergraduates as well. So if you want to just join this, it could be also an opportunity for you. So yeah, I'm so happy with this presentation. I think that this is our social media as well, and I want to share with you. You can take a screenshot right now, or email or Instagram, LinkedIn, and also website. I'll not change the page, so you can take a screenshot. And finally, my personal social media, if you want to connect, and LinkedIn, I'll be more than happy to connect with you and everyone. Honestly, solve any questions. I think that more than technical, that's for Myron. But any questions in regard to girls in quantum as well, I'm happy to tell you. So yeah, I'm so happy about that. And yeah, I think that if you want to add something, Myron, let me know. But
yes, I also want to thank you for this opportunity and this great event. I also sent my LinkedIn in the chat. Please contact me if you want something more, because I had so many more things to. So if anybody is interested, contact me. I will be happy to help. And thank you very much for this collaboration.
Awesome. No, we're so happy. Thank you so much, everyone, for joining. I hope that you can have a great evening, great morning, wherever you are in the world, and see you soon. Bye, everyone.
You too, everybody. Goodbye.